In this video, I will try to briefly introduce you to Norman Digital Sample Freezing Platform. Norman DSFP is a repository used to digitally store and screen high-resolution mass spectrometry data for thousands of contaminants of emerging concern included in Norman Compound Database. It actually consists of 3 modules. In the main page, there is the single search module, in which someone can search for the presence of a single substance in multiple chromatograms and even go back in the raw data to have a deeper look in the chromatograms and the full scan spectra. Moreover, someone can visualize the findings in an interactive map. Let's see how we can do it. As a first step, we should select the substance of interest. Someone can select a known compound listed in the Norman Substance Database by typing the name or CAS number or the standard INSI key. There are 2 additional search options: search for a mass of interest and search for a given molecular formula. In this example, we will search for diclofenac in effluent wastewater in data from the Joint Danube Survey 4. Thus, we type and select diclofenac. Once the substance is selected, the platform will retrieve mass spectrometric information such as favorable ionization, adduct, MS/MS fragments from the database, and predict the retention time index, which is the chromatographic time when a compound is expected to elute. As a second step, it must be specified the mass accuracy window, expressed either in Dalton or in ppm, and the retention time index tolerance window. There are additional check buttons for the calculation of the isotopic fit and for the semi-quantification of the detected suspects. For this example, we will enable the isotopic fit tick button. In select chromatograms, we can filter based on the project, matrix, country, and also filter the contributor data based on keywords. In this example, we will select GDS4, and filter the contributed data based on matrix by choosing wastewater, municipal, and wastewater industrial. Moreover, we will filter the results using the keyword effluent. Eleven chromatograms, 11 entries will appear, and we will select them. And click Submit. A loading bar will appear, and the platform will redirect us automatically to the results once the calculation is finished. The results show the chromatograms, followed by retention time, mass of the ion, intensity, whether experimental MS/MS is available, proposed substance, the evidence for the identity of the substance, experimental retention time index, and also list the detected qualifier ions with a specific format. This table has few more hidden columns which can appear from the button View Columns. For now, I would like to make the columns Spectral Similarity, Record with Max Similarity, and Similarity Plot appear. Since MS/MS scan is available, the system compared the experimental spectra with library spectra. And also calculated a spectral similarity score. Additionally, someone can see the mass error score and the isotopic fit score. by going to View Columns and selecting the mass error score and the isotopic fit score. There is the option to select the results. Selecting the results will enable us to go back to the raw data and visualize the findings in interactive maps. For example, if we select the first results and go to the tab Chromatograms, this will allow us to perform extract ion chromatogram. For the monoisotopic mass and the fragments in any contributed MGML file. Let's enable also the fragment 250.0184 and click the Submit button. And the extract ion chromatogram appears. The extract ion chromatogram can be zoomed and unzoomed. Additionally, we may want to have a look at the full scan spectra. For example, in this case, we may want to have a look at the distinct isotopic pattern of this substance. In this case, we select to a data point. And the full scan spectra will appear. Then we may zoom and have a look at the clear distinct pattern. If we go back to the results, we may want to select all the results, and this will enable us to visualize the results in a map. We go to the interactive map, and if we wish, we may resize the concentrations by a factor of 8. This type of visualization enables us to investigate potential sources of contaminants in a specific river basin. The second module is the batch mode module. This module enables us to screen thousands of compounds in many chromatograms. Batch mode module consists of 5 steps. Step 1, select compounds that you want to screen. Step 2, select the parameters. Step 3, select samples that you want to screen. Step 4, select blank samples. Step 5, submit your request. In the first step, compounds of interest are chosen. There are 4 options. 1. Choose specific compounds through the Norman ID. Second option is to select a compound list of interest from the suspect list exchange. The third option is to select substances that are currently displayed. And the fourth, to manually select and deselect any substances. For this example, we will go for list S06, which is a list of antibiotics created in context of the Marie Curie Answer project. 629 compounds were selected. In the second step, we specify the ionization, the mass tolerance, the retention time index tolerance, and we enable the possibility for semi-quantification. In the third step, we select the chromatograms of interest. In this example, we will go for the samples from the Black Sea collected in context of the M++ project. Thus, we select M++ and we select the 49 substances. This can be easily done by showing 50 substances and select all of them in the current page. In the fourth step, we have to specify the blank samples for each dataset. Since biota, sediments, and seawater has been collected in this sampling campaign, we need to have at least 3 blank samples. In this case, we have 4 blank samples. 1 blank sample for marine sediments, another one for biota numbered 16 until 20, another one for biota from the number 01 until 15, and another one for the seawater. We move these samples and we set them as blanks. In the next step, we specify the datasets. For the blank that is sediment, we specify the sediment samples. Then we specify the biota 16 until 20. Then we specify the biota from 1 until 15. And finally, we specify the seawater samples. If the selection is correct, this will appear. Finally, we submit our request. Once the screening is finished, the platform will allow us to download the summary. Also, we can download the summary as CSV file and also download the detailed report. Moreover, it will allow us to visualize the data in interactive heat maps. In this heat map, we can see the substances in vertical axis and the samples in horizontal axis. The more samples and the more substances we screen, the more packed is the heat map. The heat map can be zoomed and unzoomed. Moreover, we can filter the heat map for substances that fulfill criterion more than X number of fragments. For example, let's select more than 2 fragments. We can also specify substances that have predicted or experimental MSMS fragments. In case we wish to show only substances for which library MSMS spectra is available, we have to specify this query as yes and apply the changes. Moreover, we can modify the appearance of the heat map. For example, we can increase the size of the compound names or increase the size of the samples or even rotate them. This will allow us to summarize the results in one nice figure. Let's have a closer look at the summary Excel file, which is the output of the batch mode module. This Excel file consists of 6 tabs: intensity, retention time, error in millidalton, error in ppm, detected qualifier fragment ions, and semi-quantification. In the intensity tab, we can find the compound name, the molecular formula, the CAS number, structural identifiers such as SMILES, INCI, and standard INCI key, identification proofs, whether the predicted or experimental fragments are available in the compound database, and finally, intensity, signals observed in the samples. The same setup is applied in the tab retention time, with a difference that here we have the retention time expressed in minutes. Error in millidalton shows the mass accuracy error observed in the data in millidalton, and the same information is included in the error expressed in ppm. In the tab Qualifier Ions, someone can find the detected fragments in the format mass, retention time, and intensity. For example, in this case, the substance of row 11, these qualifier fragment ions have been detected for this specific sample. Finally, in the semi-quantification tab, there are some additional columns like lowest PNEC, in which trophic level the lowest PNEC was detected, accuracy of PNEC prediction. Moreover, there is information about similarity percentage between suspected compounds and the target analyte, based on which semi-quantification was performed, and the name of the target analyte. Information is also given for the units. All the given information is separated by semicolon, so that every value refers to a screen sample. For example, this value refers to the third sample. The third module of DSFP is the contribute module. Contribute module is where we can upload the chromatograms. The first input is who is contributing. To do so, someone can simply select the institute name. By selecting the institute name, this will autofill who is contributing details. This will also retrieve the instrumental metadata, as we will see in the next step. Important is that all fields remain editable. Then, the field what is contributed must be filled. In case of monitoring campaigns and collaborative trials, selecting a predefined name will autofill all the sample-specific metadata. The predefined sample names can be found in the following link. Therefore, let's input a predefined name that will retrieve and autofill all information except for the analysis date that must be specified manually. And then press Next. The next step contains sample and matrix-specific information. All has been filled for us. It is important to note that there is different metadata for different matrices. Also, it is important to highlight that Norman network experts have developed appropriate metadata for all environmental matrices. In the next step, we have to specify whether our contribution is a positive ionization contribution, negative ionization, or both. Let's select positive ionization. Again, all the information is known since we selected the contributing institute. The next tab is the retention time of the retention time index calibrant substances. This piece of information is also known, but remains editable. In the next step, we input the standard addition calibration curves that will enable DSFP to provide semi-quantitative results. This field is optional, and since it's not available right now, we will let the table as it is. In the final step, we have to upload the MZML chromatograms. This step is different based on the acquisition method that every laboratory is using. DSFP supports all possible data acquisition methods. The collision energy layers of data acquired under data-independent acquisition has to be separated before uploading to the contribute module, using a tool which is under More Tools, Split Data Independent Data. data-dependent chromatograms can be uploaded without any further modification. For the sake of the example, we will upload both types of chromatograms. In this case, we have two collision energy layers. One is 20 eV and then the other one is 40 eV. We browse the respective files. In this case, we also analyze the extract using data-dependent acquisition. Once the upload is done, we can press Submit button, and our contribution will be ready in few minutes. Please note that the button Download the data collection template will activate once the loading bar is full. Once the contribute procedure is done, we can download the data collection template. The output of the contribute module is the data collection template. The data collection template consists of 9 tabs. In the first tab, we have the organization details, which represents who is the contributing laboratory and person. In the second tab, we can find the retention time index calibrants and their retention time in both positive and negative ionization. As you may recall from previous video, we uploaded a chromatogram only in positive ionization. Thus, the retention time of negative electrospray ionization calibrants is not filled in the Excel file. The next tab is the N-alkanes used to calculate the retention index in GCMS. In the next tab, we can find the sample description. Sample identification is the name of the contribution followed by a unique identifier created during the contribution procedure. The country follows, then the name of the station, the national code of the country, longitude and latitude, in both degrees, minutes, seconds, and decimal formats. Precision of coordinates shows the precision of the coordinates, and these are the following choices available. Then we have the type of data source, which can be either monitoring data or research and technical studies or surveys, and then the type of monitoring, which can be one of the following choices. Finally, we have the title of project. This is the general information that is needed for every environmental sample, and afterwards is the matrix-specific information. In this case, it is surface water sample, and more specifically, river water. Therefore, the respective information such as fraction, name of the river basin, sampling depth, pH and temperature are available. Other useful metadata, not filled in this specific example, can be found also here. In the next tab, we can find the instrumental method information for LCMS. Since we uploaded only positive ionization chromatograms, only one row has been filled, named non-target pose. Then we see the instrument type, the model type, the analytical column and its dimensions, the solvent of the extracts, the injection volume, the column temperature, the composition of the mobile phases, the gradient, the flow, the scan range, the resolving power, accuracy MS and accuracy MS-MS, the ionization type, the different methods for the fragmentation, and the collision energy. The next tab is the GCMS tab that describes the method. This tab contains all the necessary information, and it is very similar with the previous tab. Few differences are the injection mode, the carrier gas, and the program temperature. The core of the DCT is the analysis tab. Here we can find the sample identification, the retention time in the first and second column, if this is available based on the instrumental setup, the mass to charge ratios, their intensity, any detected ion type, meaning the adduct relationships that have been detected. For example, in this case, the ion represents the ammonium adduct, and all the other ions, adduct ions, have been detected. Whether MS-MS is available, and then we have some compound-specific information, such as proposed name, molecular formula, exact mass, SMILES, CAS number, estimated concentration, level of confirmation of the identification. Moreover, we have also the component information. DSFP will provide the isotopes, the adducts, and the HRMS-MS spectra. Actually, it will retrieve the highest quality MS-MS spectra from the data. Thus, all this component cluster is summarized in the component information. The next information that we have is the retention time, the experimental retention time index, the date of sampling, the date of analysis, the link with the method LCMS, the number of peaks, the intensity cutoff values, and the MGML files contributed, separated by semicolon. For each MGML file, we also have the different data acquisition type. In the tab fragments, we list all the peaks detected in higher collision energy chromatograms. This tab is filled only in case of data-independent acquisition. In our case, for 20 eV and 40 eV. Finally, there is a tab with the standard additional and standard addition calibration curves. And this information will help us to semi-quantify any detected suspected substances.